basically.
Permutations are ordered selections without repetition of k objects out of a set of n objects. So let's write this here ordered. And the number of different permutations can be distinctly written as n factorial divided by n minus k factorial. Combinations are unordered selections without repetition of k objects out of n, and the number of combinations is given by the so-called binomial coefficient, for which the standard notation is like this, k out of n, and explicitly this is n squared over, n factorial over k factorial over n minus k factorial. So these are binomial coefficients. And they're called this way because they arise in Newton's binomial formula. I'd like to discuss this connection now. Why are they the same? So Newton's binomial formula tells you how to expand an nth power of a sum of two variables, x and y. So I will use the summation notation. I will explain what it means in a moment. So this symbol here represents summation, and the summation runs over the index k, taking the values from 0 to n on top. And what they're summing is the binomial coefficients multiplying kth power of x and the n minus kth power of y. So the summation symbol is to be replaced by an explicit sum in which we take the expressions which we're summing and substitute the values of k equals 0, 1, 2, 3, and so on up to n. Right? So for example, let's take n equals to 5. So for example, let's take n equals to 5. So then replacing n by 5, I get the sum from 0 to 5, k out of 5, binomial coefficient, x to the power k, y to the power 5 minus k. And writing this out explicitly, I should first take k equals 0. That gives me 0 out of 5, x to the 0th power, y to the 5th power, plus, when I'm doing the summation, the next term will have k equals 1, so it's 1 out of 5, x to the 1st power, y to the 5 minus 1, which is 4, plus the next term corresponds to k equals 2, 2 out of 5, x squared, y cubed, plus 3 out of 5, x cubed, y squared, plus 4 out of 5, x to the 4th, y to the 1st power, and the last term corresponds to k equals to 5, what stands on top of this summation symbol, and it will look like 5 out of 5 x to the 5th power, y to the 0th power. And these binomial coefficients can be calculated explicitly, so 0 to 5, well, that's 5 factorial over 0 factorial, 5 factorial. So 0 factorial, I remind you, is set to be equal to 1. So that's just equal to 1. 1 out of 5, that's 5 factorial over 1 factorial, 4 factorial, that's equal to 5. 2 out of 5, similarly, is 5 factorial over 2 factorial, 3 factorial, and that can be calculated to be equal to 10. And so you've got the idea how to use the formula. I'll just write out the remaining coefficients. 3 out of 5 is the same as 2 out of 5, that's 10. 4 out of 5 is the same as 1 out of 5, that's 5. And 5 out of 5 is the same as 0 out of 5, that's 1. So this gives us x plus y to the 5th power is y to the 5th plus 5x y to the 4th plus 10x squared y cubed plus 10 x cubed y squared plus 5 x to the 4th y plus x to the 5th. So that's how the formula works, and you can, so what are we doing? We're, by taking the nth power, we're multiplying n copies of the sum x plus y. So what we're doing is x plus y times x plus y times x plus y, and so on. And if the power is m, then we have n pairs of brackets. And how do you expand them by hand? Right, you would, from each pair of brackets, you would pick either x or y. Right? And for example, we can keep track of the brackets from which we take x. Then from the rest of the brackets, you'd be picking y. Right? By default, there's only there are only two choices. And for the terms, so the terms which come with the k power of x, the terms x to the k, y to the n minus k, means you pick k from n pairs of brackets, sorry, you pick x from k pairs of brackets, and you pick y from the rest of them, and there are, since altogether there are n pairs of brackets, the rest of them means n minus k, right? So that gives you the power of y to be n minus k. And so all such terms, they come, so or arise when we pick x from k pairs of brackets and y from the rest of them. So if we, so finding the coefficient in front of such terms is equivalent to finding in how many ways you can select k pairs of brackets from the set of n pairs of brackets. So, coefficient in front of x to the k, 1 n minus k, equals to the number of ways we can select k pairs of brackets from the set of m pairs. And here you can see, well, you're not allowed to select the same pair twice, right? When you span, you only pick once an element, x or y, from a given pair. You cannot pick it out twice. So in these selections, there are no repetitions. No repetitions are allowed. And the order doesn't matter, right? There is nothing. It still will be x to the power k, no matter in which order I select them, right, among those pairs written up there. So what we are dealing with is combinations. So these are combinations, and their number equals this the binomial coefficient, right? N factorial over k factorial and minus k factorial. Right? So you see that in this Newton's binomial formula, what is hidden is some combinatorial questions, right? And that's probably, if you had this formula explained to you before, probably this combinatorial interpretation was not brought forward, but it is really there. So, any questions on this? All right, and let's look at some more examples in which this formula for combinations is used. So in the first example, there are 52 cards in the deck. A hand is 13 cards. How many possible different hands are there? It's given that there are 52 cards in a deck. Hand is 13 cards, and all the cards are different, no copies, of course. How many different hands are there? So, as I just said, we have to select 13 cards out of 52. Repetitions are not allowed in the deck. Each card is unique. And the order in which you select them doesn't matter. So hand is just a collection of 13 cards, not a collection with a specific order. So we're dealing here with combinations. We have to count the number of combinations of 13 cards out of 52, and that's just given by the corresponding binomial coefficient. So 52 minus 13 is 39, and that's a huge number. On the midterm or the final exam, all such counting problems always come with a suggestion that you should express your answer in terms of factorials. So an answer like that is fine. Don't feel like you have to always get to this, down to the concrete number. Just leaving it written in terms of factorials is all right. All right, so this was very straightforward. Just recognizing that we have combinations. Let's look at something a little bit more interesting. Another example that is based on cards. A full house in poker is a collection of 5 cards in which 3 of them are from one denomination and 2 from another. There are 13 denominations and 4 cards of each denomination. How many full houses are there? Okay, so let me write this down. A full house is a collection of 5 cards in which 3 of them are from one denomination and 2 from another. There are 13 denominations. Which are the usual numbers from 2 through 10. Ace, Jack, Queen, and King. And there are 4 cards, 4 suits of each, and 4 cards of each. How many different full houses are there? Okay, so how do we solve this? So we have to select 5 cards, but not just any 5 cards. So they have to satisfy the special rule that 3 have to be of one denomination and 2 of the other denomination. So we might as well start by picking a denomination for the group of 3 cards and picking another denomination for the group of 2 cards. Right? That will have to be specified. And so we first pick a denomination for 3 cards, and there are 13 choices, right? Because there are 13 denominations altogether. So we can organize our procedure different ways. For example, I can first pick the 2 denominations and then pick the cards within each denomination. Or I can pick the first denomination and then cards within that denomination, so they'll be done with a group of 3, and then I'll do the group of 2 separately. So I'm going to do it like that. So I have 13 choices, and once I've chosen my denomination, I have to pick 3 cards out of 4, right? Because there are 4 cards in each denomination, and the order doesn't matter, right? So there's nothing specified about any special arrangement of these 3 cards, and repetitions are not allowed, right? Each card is unique in the deck. And so those are combinations, right? And we have 3 out of 4, right? Is the number to pick, the number of possible ways to pick the cards within that denomination. So it's 4 factorial over 3 factorial over 1 factorial. That's equal to 4. So there are 4 ways with the number of ways to pick 3 cards within the chosen denomination. Okay, we're done with the group of 3. We just should remember that we should multiply through all the choices, but that we'll do at the very end. So next, we pick a denomination for the group of 2 cards, and that denomination has to be different from the group of 3 cards, right? So we have, once that denomination is chosen, there are 12 possible choices for the second denomination, right? So we have 12 choices. And once we have chosen the denomination, we have to pick 2 cards out of 4. And then we have 2 out of 4. So that equals 4 factorial over 2 factorial, 2 factorial. So that's what? 3 times 4 divided by 2. So that's 6. So there are 6 ways to choose 2 cards within the chosen denomination. All right. Finally, we have to multiply through our choices. Why multiply? Because we are choosing the first denomination and we are choosing the cards within that denomination, and we're choosing the second denomination and the cards in that denomination. So that's, and none of the choices is affected by the previous choice, right? So this is the case to use the product rule. So by the product rule, the final answer is 13 times 4 times 12 times 6. That gives us 3,744. Any questions? The product rule we formulated 2 lectures ago. It's if there are n of a ways to do A and n of b ways to do B, then if you want to find the number of ways to do A and B, then that's n of A times n of B. Formulate more generally. Okay. Right, let's do one more example. So we need to select a committee. Let me, formulate the whole thing in one sentence. In how many ways can one select a committee of 10 people out of a group of 26, and select among them a treasurer, a chairman, and an administrator. Chairperson, a treasurer, and an administrator. Okay. So it asks us to do 2 things: to select a group of 10 people, and among that group to select people who will be playing 3 different roles. So, so these are 2 different tasks, and no restrictions are given, so they are not influencing each other. So the choice we make for which people are there will not limit our choices of the three positions. So we can separate these two tasks, right? Count separately the number of ways in which they can be done, and then use the product rule again. And in the first task, we're just selecting a group of people, 10 out of 26. Repetitions are not allowed. You cannot select the same person twice. It's just a group subset of people, so the order doesn't matter. We know that these are combinations, and therefore the number of ways to select 10 people out of 26 is given by this binomial coefficient, right? 10 out of 26. So that's the number of ways to do the selection, and then amongst those 10 people, we have to fill in these three positions. We had separately this type of example, and that's an example where the order matters, because, well, for example, we can decide that first we select the person for the position of the chairperson, and then for the treasurer, and then the administrator. If you reshuffle those people, those three people, it's a different choice. So the order does matter. So we count different orders separately. And that is a permutation, right, of 3 people out of 10. So the number of such permutations is 10 factorial divided by 10 minus 3 factorial. Since we have to do both tasks, as I discussed at the very beginning, we have to multiply these numbers. And now we write out explicitly in terms of factorials, so we get 26 factorial over 10 factorial and 16 factorial, that's the binomial coefficient, times 10 factorial over 7 factorial. We can brush this up a little bit, just cancel, say, 10 factorial here and there, and arrive at this answer, which then could be plugged into a calculator to get a definite number, but we're not going to do it, so we can stop here. That's the answer. Any questions? Yes?
Repeat again a little bit.
Sorry, repeat.
The 10 factorial, 10 minus 3 again.
So the first factor corresponds to choosing a group of 10 people out of 26, the first task. The second factor corresponds to choosing 3 people, choosing a selection of, an ordered selection of 3 people out of 10. Right? So these are combinations, and these are permutations. For permutations, we have that formula n factorial over n minus k factorial. Right? When we select a group of k out of group of n. So here we're selecting 3 out of 10. So n is equal to 10 and k is equal to 3. That's why I wrote here 10 factorial over 10 minus 3 factorial.
Yeah, the combination. You remember yesterday I asked why can't we choose the administrator first and then the chairperson between? Does the sentence imply that we have to choose them in that order?
Well, we're choosing. We can agree on, you know, on the ordering, what the ordering means. Right? That's a convention. For example, we can agree that we order these people, and the first will play the role of chairperson, the second will be the treasurer, and the third will be the administrator. Right? So that's how we fill in these positions. And that's the same as picking ordered selections of 3 out of 10. And other selections, those are permutations, in other words, and the number for them is 10 factorial over 10 minus 3 factorial. Yeah. So I have two tasks here. One is an ordered selection, just selecting the group, and the second one is the ordered selection when I'm filling in the positions. Well, you have to, because if you reshuffle, people say John is doing will be the chairperson, and Jack will be the treasurer. If you swap them, that's a different choice. So the order matters. Yep. Everybody okay? All right, then let's move on. We will learn one more counting technique, which is called the inclusion-exclusion formula. Inclusion, exclusion, and there will be two versions formulae. Now start with the simplest version. So for two sets, really destructive when somebody whistles. You can ask please not to do it. For two sets, the inclusion-exclusion formula reads like this. It tells you that the number of elements in the union of two sets equals the number of elements in the first set plus the number of elements in the second set minus the number of elements in the intersection. And this can be illustrated on a Venn diagram. So in general, you have two sets, A and B, then the Venn diagram looks like this. And if you just take the number of elements in A and add to it the number of elements in B, then there will be certain elements in the union which will be counted once. So the elements which are in A but not in B will be counted once. They will be only part of this number of elements. Similarly, the number of elements which are in B but not in A will only be counted once, because the intersection is a subset of A and a subset of B. And so to correct for that, we just subtract the number of elements in the intersection with coefficient 1. So since they were double counted, now they will be singly counted. If I do that subtraction, then each element in the union is counted exactly once. Okay, so I arrive to the total number of elements in the union. From the point of view of combinatorics, this formula is a corrected sum rule. This formula is a corrected sum rule. So the sum rule says that if there are n of A ways to do A, and distinct from them n of B ways to do B, then the number of ways to do A or B is the sum, right? So the sum rule corresponds to looking at the number of ways to do A, which is one set, number of ways to do B is another set. Since they're supposed to be distinct, that means there's no overlap. And that means that the number of ways to do A or B, and this is how we look at the elements from the union, they belong to A or belong to B, that's just the sum in this case. But in general, if there is an overlap, there is a correction term to account for that. So let's look at an example of how this formula can be used. find the number of cards in an ordinary deck that are clubs or aces. Clubs or aces. So there are four suits, right? Clubs is one particular suit, and aces is one particular denomination, right? There are four cards of each denomination. So what are the sets here? We can denote as A, the set of all aces in the deck. And there are four of them. So the number of elements in A is 4. And we can denote by C all clubs. And there are 13 of them, right? Because there are 13 denominations. And in terms of these sets, what we're asked to find is a number of elements in the set, which is the union of A and C. Because the union is precisely implements this logical OR. Cards which are aces or clubs or aces. So by inclusion-exclusion formula, this equals to the sum of elements in A and C minus the number of elements in the intersection. So we know the number of elements in A and in C. And what about the intersection? The intersection consists of cards which are simultaneously aces and clubs. And there's only one such card, which is the ace of clubs. So A intersection C contains only one card, which is the ace of clubs. Okay? So therefore, the number of elements in the intersection is 1. Substituting these three numbers, we get 4 plus 13 minus 1, which gives us 16. So there's 16 cards, which are clubs or aces. Let's do another example of a different type. How many integers from 1 to 500 are divisible by 3 or by 13? That's what we're supposed to count. How many integers from 1 to 500, and including 1 and 500, are divisible by 3 or by 13. Okay, so let's first formalize this problem in terms of sets. So firstly, there are numbers which are divisible by 3. So let this be the set A, right? So that consists of integers n such that, well, the integer n has to be between 1 and 500. And, well, n is divisible by 3 means that it looks like 3 times some other integer, which I'll call n. Right? And explicitly, this will contain the numbers 3 itself, or 3 times 1, 3 times 2, 3 times 3, 3 times 4, 3 times 5, and so on. Right? We can figure out what the last one is. but I'll do it in a moment. But for now, that's just me defining the relevant sets. So this contains all the numbers divisible by 3. Right? And it looks like 3 times the integer. So I can list them. And let's also introduce the set of numbers between 1 and 500 divisible by 13. So n such that n is between 1 and 500, and then equals 13 times some integer. Again, we can list them as 13 times 1, 13 times 2, 13 times 3, and so on. Okay. So now, having introduced these two sets, we already know what we're after. So we want to find numbers which are divisible by 3 or by 13. That means that they're either in A or in B. And that's again a logical OR. So we want to find the number of elements in the union, A union B. Okay, now that we know what we're after, we can see that, well, we can use the inclusion-exclusion formula. Over here. By the inclusion-exclusion formula, number of elements in the union AB equals number of elements in A plus number of elements in B minus the number of elements in the intersection. So we need to figure out how many elements we have in A, right? And we have already started on describing A explicitly. We need to find the number of elements in B, and then we need some description and the number of elements for the intersection. So let's do one thing at a time. So let me first find the number of elements in A. So here, writing out them explicitly like these, as 3 times 1, 3 times 2, 3 times 3, and so on, already tells me how I can count them, right? Because the second factor can be considered to be just the as counting them, right? So the first element, the second, the third, the fourth, right? So how many elements I'll have together? I'll need to figure out what's the last element there. And then if I divide it by 3, that will be the number of all elements in the set A. And so the last integer, which is less or equal than 500, which is divisible by 3 is, well, if 500 was divisible by 3, then it would be 500 divided by 3, right? Because 500 divided by 3 times 3 equals 500. That would be the last element. But since this is a fraction, I need to round it, because we're talking about integers, right? The last integer, which is divisible by 3. So rounding is denoted like this, and here I take the integer part. So I'm rounding to the closest smaller integer, right? So this where the brackets stand for the integer part. Of the number. And we can calculate this using the calculator. 500 over 3 equals 166.66. So, and to infinity, so the integer part of this is 166. And we can check ourselves. 3 times 166, that's 498. If we take the next number, 167, then 3 times 167 will be that number plus 3, which is 501, right? So that's an overshoot. That will not be there. So the last number divisible by 3, which is less or equal than 500, is 3 times 166. And therefore, there are 166 numbers in the set A. Therefore, the number of elements in A is 166. Right? Because they're precisely labeled by the second factor. Okay, now we can use the same idea to calculate the number of elements in B. So by the same token, the number of elements in B is the integer part of 500 divided by 13. Right? Again, the numbers are labeled by the second factor. So 13 times 1, 13 times 2, 13 times 3, and so on. And the last integer in that sequence will be 500 divided by 13 times 13, and with the integer part taken. So using a calculator, we get here 38. And again, we can double check ourselves that 38 times 13 is smaller than 500, but 39 times 13 is larger than 500. That can be checked as well. And finally, let's discuss the intersection. Okay, intersection B is a numbers which are divisible by 3 and are also divisible by 13. And since 3 and 13 are relatively prime, they don't have any common factors, such a number should be divisible by 3 times 13. Okay? So since 3 and 13 are relatively prime, they also happen to be each of them prime, but what's important is that they're relatively prime. Such numbers have to be divisible by 3 times 13, which is 39. Okay? And now we can use the same consideration as before. We can find all the numbers between 1 and 500 divisible by 39. Right? Their total number will be 500 divided by 39, integer part taken. And so using calculator, this is 12.82 ... But remember, we are not rounding to the nearest integer, but to the nearest smaller integer, so which means dropping the fractional part. So that is 12. So that's the number of elements in A intersection B. Okay, so we found all 3 ingredients. Now we use the inclusion-exclusion formula and just substituting the numbers. We have 166 plus 38 minus 12, which gives us 192. Any questions, please, about this example? Yes. Well, 3 and 13 are relatively prime. Relatively prime means 2 integers which don't have any common divisors except for number 1. Well, in this case, they're 2 distinct prime numbers, so definitely they don't have any common divisors. If we had different numbers, different than 3 and 13, which would have common dividers, we would need to account for that, right? We would need to correct, but using the same set of ideas.